focus of my presentations for this week in MDA 101 will be about relations and mappings. You see, this is coming back to the language of mathematics, or let's say mathematics as a language, and that's a layer of what we have to absorb to be really mathematicians, or at least close to. The first concept I want to talk about is the relations. So relations is a very general scheme. So you simply take two sets. I think we don't have to bother about which set theory we are in, because everything will be rather driven by our common sense than anything else. But perhaps we know what sets are for us. So that let's take two sets A and B, and their Cartesian products is simply a set of all couples. Take anything from A, anything from B, and we have got the couple AB, right? And a binary relation is simply a subset of the Cartesian product, any subset. And that's a general tool to indicate that we have some reason to consider these couples AB, which are in the subset, and as having some relation between them, nothing more than that. And there is the domain, there is the codomain, so it's very similar to maps, except maps are a very special case of this. So for the maps, we simply write as we are used to. F goes from the domain to the target, to the image, and we can write it the way we've been using already for quite a while. So there is the concept of being surjective, being injective, which means either you hit everything, that's the surjective, or you never have the same value for two different arguments, etc. So what we were drawing as images is in this language called the graph of a mapping, and the graph of a mapping consists of couples, the argument, and the value, right? And so you see that it's a special case of the relations, and the relation corresponding to a mapping is actually what we call its graph. And not every relation is a mapping, of course, because you can have two images related to the same source, right? And then it can't work. So the relations can be composed exactly as mappings, so you can see it in the definition. So simply, if you imagine the relations as being drawn by such arrows from the domain to the target, then composition of the things mean that you can find a path from the thing here to the thing there, right? So it's again very, very simple idea. And you also have got the inverse relation. So every relation has got the inverse, and the inverse relation is built in such a way that we simply swap the order. So instead of AB, we write BA. So that's again very straightforward. There is a special class of relations which are of the greatest interest, and that's if A is the same as B, and then we are talking about relations on a set. So our set is the set A, and we are questioning which couples from the same set are in some relation from our perspective. And there are some special features of such relations which have got their names because they are appearing again, and that's the reflexivity, where we insist that the diagonal is always there. So for every A is in relation with itself. It's symmetric. It means that with AB there is also BA there. So the inverse of R is the same as R. Antisymmetric, it's just the opposite. So the inverse intersects with R at most at the diagonal, right? So the intersection is at most the set of couples where A equals B. But it doesn't say that they must be there, right? It could be also empty, the intersection. And transitivity is the most important one perhaps, or another very important one, and that says that if I have in the relation, if A is considered to be related to B and B is related to C, then A must be also related to C. So that's the transitivity. And of course, this makes sense because that's modeling what we usually meet, right? And then what we meet most often is what we call equivalence. For some reason, I will simply take as equivalent all the couples which are from some point of view the same. Like, for example, if I look at sandwiches on a shelf, so the sandwiches of the same time will be called equivalent, right? So although they've got different barcodes and different numbers there, but they are equivalent from the point of view how I view them as a type of sandwiches. And then of course it must be reflexive, because everyone must be equivalent with itself. It must be symmetric, because I don't want to see that the first sandwich is equivalent to the second one, but not vice versa. That would make sense, right? And I want also the transitivity. So that's the equivalence relation. And in some sense, one of the sayings is that you will become a mathematician once you adopt the concept of equivalence, and you will be able to deal and handle things of the classes of equivalent objects, understanding them as a new object of your interest. So and handling them by viewing at any of the choices of the particular ones, right? And we shall come to that. That's a that's the main feature of equivalences, which makes them so useful. Another type of relations is ordering, which is nearly the same literally, but completely different in fact, because if you deal with an ordering, it's something like ordering of magnitudes or ordering on natural numbers or whatever. So we say that A is less or equal to B, and we want to have the orderings reflexive, transitive, and antisymmetric. That's clear, because if A is smaller than B and B is smaller than C, then we want to know the same relation between A and C. And if A is smaller than B, then definitely we don't want to see that B is at the same time smaller than A, except they are equal, right? So that's the antisymmetry. Right, so this is the main two classes of relations. So we said that an ordering is complete if we can say for every couple whether A is smaller than B or B is smaller than A. And we shall see in my lecture for the MDA 102 that this is just a very important thing which we want to see on real numbers, to have an ordering. And we can't get that, a complete ordering, which would be compatible with the arithmetic operations on complex numbers. So that's something we shall come to in a moment. And yes, and the feature of equivalences I was talking about is the fact that each equivalence provides you with a partition of the set on which the equivalence is defined into the classes of equivalent objects, or equivalence classes. And that's a very important thing, as I tried to explain already. So a mathematician knows how to or takes as absolutely standard and normal to view objects up to equivalence. So the equivalence classes become new objects of interest, and you can handle them via representatives. That's exactly what we need, and it's very easy to get them. You simply pick up, so imagine you have such an equivalence. So what you do is, in a computer for example, you pick one element from your basic set A, some A like this, and then you look at all B's in A which are equivalent with A, and you put them, you collect them to a folder, right? And once you can't find any other ones, you've got all the equivalent ones, and then you can have a look at A. If there is something remaining, you start with that one and again find all the equivalent ones and you get the next folder. And in the end of the procedure, all the folders will be just the classes of equivalences. So the equivalence classes. Right, and now we can come to an example how to work with these things. And that's something which is very important by itself, because in mathematics, as we already have seen, we like to work with the simplest possible set of properties, which we call axioms for some given type of objects. And then the advantage is that we know that all the other properties we are interested in are already consequences. Then it means that whenever we find some other class of objects which would satisfy the axioms, we know that all the theorems, all the properties we are sure about will hold true for them as well. So that's very important. And at the same time, if we start with such a set of axioms, then we should be sure that in our, say, understanding of mathematics, starting with some set theories or knowing what sets are, if it's based on sets, we should be sure that such an object exists. So we know that for the theory there is at least one object which satisfies the axioms. It's well known, and it's a general matter of logic, that if it would happen that it doesn't exist, then in such an empty theory you can prove any claim, right? So that would make sense. So our first thing is to make sure that there are the most natural scalars, and these are the natural numbers, right? And there is a way how to build them, one of many ways, and our is that we build them just to use our, say, language of mathematics and follow the fact that we want to have the naturals as something which counts the number, so how many objects are there in a set, right? So we start with an empty set. We assume that we know what an empty set is. That's always in mathematics like that. You always have to assume something and then you can deduce. So for us here, we assume that we know what the sets are, right? So empty set is a well-known object, so let's take this as 0. And then we inductively define n plus 1, so the natural, which is 1 bigger than the previous ones, as the union of the set of the n, of the object n, with one new object, and that would be the one element set containing only n, right? So you see, in this way, 0 is simply the empty set, 1 will be the one element set containing the empty set, 0. Well, that's a different thing. You have a one element set and the only element in that set is the empty set. Why not? Sounds weird, but why not? 2 is the set of the two previous ones, right? So it's the one element set. So it's the union of the empty set and the so what it would be actually, so 2 is the union of this guy, so that's the 1 and 0, right? So this would be 1. This would be 2, right? So it's exactly according to the definition, and we can go on. So 3 would be more difficult and so on, and we can also write it this way in a nice inductive procedure. So this is the definition of the naturals. And now of course we have to take care and define what the multiplication and addition would be. So I leave it for you. Also, the text doesn't say it very explicitly, but there is an indication how to understand it. And then, of course, we have to check that all the axioms hold true. So that would be, again, a lot of writing if you would want to explain it word by word in all details. But it seems obvious, doesn't it? Right, so that's the naturals. And one of the important thing is that it's built in this inductive way, and it produces then something which we call a countable size of a set. So all the sets which have got this property, they can be mapped bijectively to the naturals, are called a countable set. Right, so here you see how it works. So we say, for example, that's the plus and times, and then we want to define the ordering, and the ordering is very easy, because we can say that m is less than or equal to n if m is included in n as a subset, which comes directly from the definition. So that's very, very easy, and you see one example here. Right, so these are the natural numbers. So what to do with the integers? So what are we missing in the natural numbers to get the integers? We miss the negative numbers, because if n is bigger than m, so m minus n doesn't exist, right? So there is nothing which, if you add m, would give you n, vice versa. So right, so what we can do is we can help ourselves now with the concept of the equivalences, right? So we say that actually, so what's the problem? Instead of talking about differences of natural numbers, we can simply say that the difference is given by choosing the couple, where a is given and b is what I want to subtract, right? And now, of course, if I take two couples like that and I shift both by the same, so I add the same natural number to both of them, then I should get something which provides me with the same difference, right? That makes sense, that's what we expect. So we can say that that's exactly our equivalence, right? And of course, we can't write it this way, because these things do not make sense, but because we know that the algebraic operations we want to introduce on the newly constructed integers should obey all the rules, so we know that this one must be equivalent to this one. And this one makes sense, right? So a plus b dash must be the same as a dash plus b. And that's the relation we define. We check that it's an equivalence, and then the integers are the equivalence classes of those things. And you can read through and see that this makes sense, and it also provides you with the only way how to define the operations there, and all the properties will hold through. So it's not difficult to go through, and then we do exactly the same with the quotients, right? So if you deal with the integers, so how to construct the rationals? Well, you simply tell we are interested in the quotients. So what are the quotients? They are given by the couples, but different couples provide you the same result. So you want to see this, but this doesn't make sense in integers. So you can rewrite it this way, and this is a well-defined equivalence, and everything goes through again. So that's a quite nice thing. The same thing then works for the remainder classes, right? That's something we also saw already. So with the remainder classes, we simply are not interested in integers as such, but we are only interested in what's the remainder after division by some fixed natural number k, right? And what we get is the equivalences, because we say that two integers are considered to be the same, to be equivalent, if the remainder after the division is the same. And now you can work easily by picking up the representatives, because all the arithmetics work in a commutative way. It doesn't matter whether you first look for remainders and then do the operations with the remainders and again look at the remainders, or if you do all the computations in integers and only the result will be then checked what's the remainder and which class it belongs to, right? So these are the reminder classes, and it's a nice thing, and we can't prove it in all details. It will need some more care, but you can either look in the later chapter, or you can believe what I use, and you see that if k, the chosen integer defining the remainder classes, so the k, if it's a prime, so it doesn't have any divisors, so it just divided without remainder, only by itself and 1, then the result is a field. So it has got all the rules we wanted for the reals and rationals, and it obeys them. And that's exactly how the computers work. So they have some pretty big k, and the arithmetic is run in that, and there are some ways how to understand what happens if the numbers are much bigger than that, right? But it's possible to do it this way. So that's what I had to say for this week. Thank you for your attention, and see you with the next one.